Well, now you know your ABCs of Smith charts. But there is much more, much too much to present for now. But we can move ahead, nevertheless, to your amazement. The depth of the Smith chart boggles the imagination with the unseen data that it makes available to us. Consider, for example, conductance, which is the reciprocal of resistance, a term or component that is often used in electronics. And this should not intimidate you. Conductance is your friend. It's here to help you. You remember resistance. Conductance is the inverse or reciprocal of resistance. 1 divided by the resistance is conductance, referred to using the term G. It is really helpful in electronics to be able to talk and converse in conductance. Therefore, it would be very nice if the Smith chart could tell us about conductance. It would be nice if the Smith chart could also have lines showing us conductance. Remember, conductance is your friend. So we want those additional lines, and you should not think of them as an object to grapple with. Conductance is given in units of Siemens. So here you are thinking that this is going to be really hard when it's really simple. Okay, let's take an example. How many Siemens is 1 ohm? Well, let's think. Maybe I did pick a really hard example. Let's see. What is 1 divided by 1? Let me think. Admittedly, that was a tough one. Let's try one that's a little easier. How many Siemens is 2 ohms? Well, the answer is, what is 1 divided by 2? I don't know, maybe that was a little hard. So this is where Smith's chart will come to the rescue. Wouldn't it be nice if Smith's chart could just simply give us those lines of conductance? And how did the Smith chart go about doing it? All it did was just take those resistance lines and rotate them 180 degrees, and bingo, here are the lines of conductance here to help you. The important thing to take home is that you already knew that these lines were here. You just couldn't easily identify them. You already knew that they were there. Are you ready to take this to the next level? Now that you know your ABCs of the Smith chart, let's learn how to move your ABCs. Think back. What is the Holy Grail that you learned about earlier with the Smith chart? The Holy Grail is finding a path home. In this example, we have measured a vector impedance of our antenna, and it falls on the space marked by the dot. The impedance is inductive, so capacitance needs to be added in order to move towards home plate. There are 2 avenues available to move south. One is resistive, which will take it to home plate. The other avenue is conductive. While it does move the vector impedance in the capacitive direction, that avenue is not of any help in this case because it does not move it any closer to home plate. Suppose that our antenna measured with a capacitive vector impedance. As in the earlier case, there are 2 paths to cancel the capacitive effect. One is a conductive path. This helps, but does not move us in the direction of home plate. The other is a resistive path. The resistive path in this case takes us home, the Holy Grail. Are you ready for an all-new concept? To this point, we've talked about lines of conductance, and we've talked about lines of resistance, and we've talked about real numbers, and we've talked about imaginary numbers. But there's something new that we have not presented yet, and it's been there all the time, right in front of you, and you never saw it. Look at the big, bright outer red circle. That circle represents time, but we call it phase. It's a relative phase. One trip around the entire circle represents a half wave. But why a half wave? Well, the answer is because that's the point where it repeats again. For transmission line purposes and Smith chart purposes, we're only interested in absolute values, and the only thing that's different between the first half of a wave and the second half of a wave is the polarity. How fast does electricity travel? It travels almost at the speed of light. Therefore, how long does it take electricity to travel a length of wire? How long does it take electricity to travel down a longer wire? The answer is, it takes time in the first case, and in the second case, it takes a longer time. Prepare to receive an all-new concept regarding the Smith chart. This concept will be incredibly valuable to you. As you add transmission line length, you increase the phase difference, or in other words, you increase the time that it takes to travel the entire length of the wire. Adding 1/8 wavelength brings you up 90 degrees in the circle. But here's the important thing to recognize about what is going on. As you add coax length, the vector impedance point changes, but in changing, its distance from home plate remains constant. The vector impedance circles home plate. While the distance as the crow flies to home plate does not change, adding coax does change the vector impedance